Okay, so we've been talking a lot about this pot of water, right? In your styrofoam cup, in an actual pot of water. And about this pot of water was everything you just told me. Kinetic energy, it was about this formula, Q equals what?
MC delta T.
MC delta T, where M is?
Mass.
C is?
Specific heat energy.
And the triangle, which doesn't look like a triangle.
Change in temperature.
Change in temperature. Good. And that gave you Q, and Q was heat, energy, or kinetic energy, or all that sort of stuff, right? Okay, so that was last week. 2 lessons last week. All the experiments we did was about the thermometer in the styrofoam cup last week. But what was making, in your styrofoam cup, in your experiments, what was making that temperature change happen?
They bump together. Is that weird? Nope.
Well, that's what transferred the energy through.
Yeah.
But what started the bump? The person dancing.
No.
The person dancing in the styrofoam cup. Remember I was talking about that? Person dancing, bumps the next person, bumps the next person. Before you know, they expand up the train carriage. We talked about that, right? What made that person start to dance?
Breaking apart the bonds.
What bonds?
Molecular bonds.
What bonds?
Intermolecular for so
No.
hydrogen.
Okay, go to your styrofoam cups from your experiment. What started that thermometer moving? No,
Adding
the substance.
adding a substance. A reaction. A chemical reaction, right? So you know in Science 10, where you had to look at an egg frying, maybe not physically, but a picture of one, and they said, is this a chemical change or physical change? Do you remember that? This is what that was leading up to, right now. So all of this is about physical changes. And you went and measured the heat of the physical change. But what caused that physical change to happen? A chemical change. So let's go to our pot of water instead of our styrofoam cup for a minute, because then we can keep it nice and separate. And let's put our pot of water on a stove. Okay, so here's a stove, and let's make it a gas stove. And so there's the flames underneath our gas stove, heating up the gas stove. Okay, what gas comes into your gas stove? Really? This is Alberta.
Methane.
Methane. Methane. Methane. Methane. Okay. So, what is the symbol for methane? CH4.
Oh, crap.
And what are you doing to that CH4 in order to make those flames?
You're splitting it. You're plus O2. So
you're combusting it, reacting with O2. So plus O2. And you're getting CO2 and H2O. And balancing that, I would need a 2 here, and I would have 2, 4, so I need 2 there. Okay, so this is a chemical reaction, right? And this chemical reaction is breaking these sticks. I mean, if you think about the molecules on the roof here, you're breaking the styrofoam balls apart from each other, and you're sticking them together in a different Lego arrangement that is CO2 and H2O. And that breaking of bonds and forming of bonds nets an energy. In this case, it's going to be exothermic, right? And all that energy then went up into your pot. Everybody get that? This, because it's a different kind of energy. It's a chemical energy, a chemical change. We have to call it a different name. We can no longer call it heat energy or kinetic energy. We now call it a specific kind of potential energy. And there's a potential energy for combustion and formation and decomposition and all sorts of things. And we're going to call them all, and I think this is off the screen now, so I'm going to write it over here. We're going to call them all, in fact, through here, enthalpy. Okay, so there's a big H in enthalpy, so maybe you can remember that that's why we give it the symbol H. I don't know if that's actually why they give it the symbol H, but it's good for us to memorize that. So enthalpy with a big H is what we're going to call this type of energy. Okay, so you've got to keep them separate in your head. If I'm asking you about enthalpy, you're right away thinking about reactions. Look, reaction, circled, reaction, underlined, reaction, over here again. This is all about reactions. This is all about that methane burning. Last week was all about just a pot of water heating. Just a kinetic change, no big deal. You with me?
Yeah.
Okay, so enthalpy of a reaction, or energy of a reaction. This is all about reactions. The molar enthalpy of a reaction refers to the quantity of heat released or absorbed by a chemical reaction for 1 mole of a substance. Okay, so we've got this fancy little molar in front of our enthalpy. So we know enthalpy is about energy released or absorbed in a reaction. Molar enthalpy is about 1 mole of that thing being released or absorbed. So in my methane that's burning underneath my pot of water, I have 1 mole of methane reacting with 2 moles of oxygen to give you 1 mole of carbon dioxide and 2 moles of water. Do you remember that? Do you remember that these big coefficients actually meant something? They meant moles, and it was a ratio of 1 to 2 to 1 to 2. So here I have 1 mole of methane. Okay, and let's say this gives you 1,000 kilojoules per mole of methane. How much would 2 moles of methane give you if you were burning it? Samantha? 2,000. 3 moles of methane would give you 3,000. Half a mole of methane would give you 500. What if you found that you only produced 1 mole of water? How much energy would you have produced? 1 mole of water. How much did 2 moles of water produce? 1,000. This equation, 1,000. So giving out 2 moles gave out 1,000. So 1 mole of water would give out 500. See how we can play with that a little bit? Because it's molar enthalpy. All right. So we give these little symbols, H being the energy, the heat energy, not heat energy, the chemical energy. This little funny subscript, which looks like this, it's a Greek symbol, theta, I think. And it stands for standard, temperature, pressure, and concentration. Okay? When you did your styrofoam cups, did it maintain a standard temperature of 25 degrees Celsius? Oh, no. Did it maintain a pressure of 1 atmosphere? I don't know. And the concentration is 1 mole per liter if you have like your acid and the base and whatever else we used yesterday that was a solution. 1 mole per liter is the concentration. So when you're a real scientist and you're putting those values in data booklets that you did yesterday, if you were to put it in a data booklet, you'd have to make sure you had a standard temperature and pressure so that you could add it to the data booklet of values full of standard other things. Okay? So you see that symbol a lot. The C obviously stands for combustion, and the F obviously stands for formation. The formation molar enthalpies are in your data booklet. Open up your data booklet to like page 4 or 5 or something like that. And you see 2 whole pages full of molar enthalpy. See there? Do you see them? The title of that page says the standard, meaning that whole 1 atmosphere, 25 degrees Celsius. Standard, molar, meaning per mole. Enthalpy, meaning the energy given off or taken in. Of formation. What's formation again? What is a formation reaction? It's not combustion, right?
2 forming
2 forming into 1. 2 what? Be specific. 2 elements forming into 1 compound. So let's just take this top one here, aluminum oxide. What must the formation reaction of aluminum oxide be? Al plus O2 gives you Al2O3. And how much energy does it say that when I do this, do I actually get out of it?
-1,675.7.
Okay, well, I better look, because I didn't actually hear you muttering. Okay, 167.5.7 kilojoules. Molar enthalpy. What did that mean? What did molar enthalpy mean?
1 mole.
1 mole. 1 mole of what? Of the O2, of the aluminum?
1 mole of the aluminum.
The compound created, the aluminum oxide. So, remember in Chem 20 I made you balance with fractions? Remember that? This is where you have to do it. So, I have to keep a 1 there. Because this says, this is how many kilojoules per mole of aluminum oxide. That's what the data booklet says. So, all my balancing has to allow me to keep this a 1. Okay? So the aluminum is quite easy. 2 and 2. No problem. Oxygen?
3 over 2.
3 on this side. I need to make my 3 out of 2, and Nick, we do 3 over 2 to make my 1/2 oxygens. So those of you that avoided fractions like the plague last year, it's coming back to haunt you. But don't worry, because you're a whole semester smarter now. So you should be easy. Okay? So, if you hate these fractions, just listen to this. I have 3 on the right-hand side. I want 3 on the left-hand side. And so 3 over 2, because that's 2. And then it'll always work out. Okay? Because 3 over 2 times 2 is 3. So 3 and 3. So if I want 3, I just put 3 over 2. If I want a 9, I'd put 9 over 2. If I want 25, I put
25 over 2.
That's right, and it always works out. Okay, so if you hate it, you can always just kind of do that pattern and pray to your gods that it works. Okay, so 1 mole, what else did I want to say? I think that's it. Okay, so what does the negative mean?
There's a negative output of energy.
Pardon me, Nick?
Maybe a negative output of energy.
A negative output. What has lost energy? What are we talking about when we talk about enthalpy?
The compound.
The compounds. Very good, Gabby. You're on the ball today. The compounds have lost energy. So the compounds have lost energy. Who's gained that energy?
The atmosphere.
The atmosphere, the surroundings. Oh dear. The atmosphere, the surroundings, the pot of water even. The thermometer even. So what gained it is the Q equals mc delta T bit, but what lost it are these compounds. So negative means exothermic. Because the chemicals have lost energy. Okay? And the positive?
Endo.
Positive must be, yes, opposite charge must be opposite thing. So the positive, there's no positive on the board yet, but we'll just put positive energy must mean endothermic because the chemicals gain energy. What if so this was formation of aluminum oxide, right? What would decomposition of aluminum oxide look like? What would the formula, what would the reaction be for that? What would the balanced chemical equation be for the decomposition of aluminum oxide?
Wouldn't it just be the same ones up top except that arrow would be reversed?
Right. It's exactly the same, but reversed.
It's weird.
Everybody okay with those?
So could you just do that arrow where you just do like the both sides so you wouldn't have to
No,
rewrite
you
it?
can't.
No,
That means
okay.
something different.
Alright.
So what do you think about these charges?
Now they switch.
How much energy, so if this is how much energy I produce when I'm making aluminum oxide, how much energy do you think you have to take in when you are decomposing aluminum oxide?
Same amount.
The same amount. So also 1,675.7 kilojoules per mole of aluminum oxide. But this time, instead of being negative, energy given out, I now need to take that energy in, and so it is positive. And unlike math, we actually put our positive in because it means something. It's not just a number above 0 on the number scale. It means endothermic. Okay? Where have you seen this switcheroo thing before? In Science 10 and any biology course you've been taking, which you also need to know for Chem 30, so that's why I'm saying it right now. The exact opposites, a reaction that's exact opposite in biology.
Oh. Yeah. Photosynthesis.
Photosynthesis and
Respiration.
cellular respiration. So we take in glucose and we take in
CO2.
oxygen and we produce CO2. And if you go
Plus
on a window,
H2O.
you produce H2O. Did you know that that's where the huff comes from? It's actually your water vapor in your breath. Okay, so, and we also produce, why do we eat? Energy. Okay. And the exact opposite of that is, well, plants take in carbon dioxide, take it, I need to balance it, sorry, 6 and 6, and therefore how many oxygens? 12. The 6 here are already occupied here, so you need 12 to be the leftover here, so a 6. So I need that, becomes C6H12O6 plus O2, 6 of them. And, what size energy go on for photosynthesis?
The second,
On the left, because they have to require energy.
Well, first of all, plants take
And energy.
sunlight energy in. Second of all, it's the exact opposite. So energy must not be produced as it is here, but rather part of the reactants over there, taken in. Okay? And in cellular respiration, let's say the energy that's produced, is it exothermic or endothermic cellular respiration?
endo.
Exo. We produce energy. We give off energy. So it's exothermic. And the symbol would be negative, I don't know, let's say 2,000 kilojoules per mole. I should really look up that value one day. And so how much energy must plants have to take in per mole of glucose that they make?
1,000 kilojoules.
2,000 as well. Only this time it's not negative, but rather it's positive. Make sense? So there's actually now 2 ways of writing this. There's the way we've been writing it, this 2,000 on the side. And then there's this way that you've seen in biology where the E is part of the equation. And here is actually 2,000 kilojoules plus 6 carbon dioxides plus 6 waters. And over here would be producing 6 carbon dioxides, producing 6 waters, and producing 2,000 kilojoules. So that's your second way, and these are in your notes, I just need to scroll down a little bit. This is the second way of displaying or communicating delta H, enthalpy. Yes?
Would that be negative or no?
In math, if it's on the right-hand side of the equation, it is negative, and it's expressed as a positive on the right-hand side of the equation. Remember that? Is that ringing any bells?
No.
If it's produced, because it's exothermic, it's a product, and it's added to the other products. Does that help?
So, if it's in the equation, it just doesn't have a negative?
Well, first of all, we never have negatives in chemical equations, ever.
Okay.
Right?
Alright.
And if you were to add a negative in math, like let's say you have x equals y, and you needed to add negative 2,000, you would go adding negative 2,000, which is the same thing as plus 2,000 on the other side. You with me? Doesn't really matter how you think of it. Like, people that love math and love algebra, look at that and go, got it. People that don't love math, that love logic, are going to go negative 2,000, produced, exothermic, produced, therefore it's a product. So I added a little product. Positive means I took it in, so I start with it, so therefore it starts as a reactant. And those of you that don't like either, simply just have to memorize negative right-hand side, positive left-hand side. So you just kind of need to figure out which one makes sense to you and then do it that way. Okay? Okay, so where are we going with this? I kind of skipped around this whole booklet, really. I did a much better job last class of making sure I went through the whole thing. We've done this. So this is talking to us about what's the molar enthalpy change for the following reaction. So here it is here. If they tell you it's this many per mole of sulfur dioxide, and in this balanced chemical equation I have how many moles? 2, not just the 1. So I must be producing 2 times that energy. And so therefore I have almost 200. So if 1 mole produces 100, then 2 moles will produce 200. See that? Okay. So those are the first 2 ways that are listed here, like 1 and 2. Within the equation as a product or reactant, or after the equation like we did here. Okay? What does the delta mean? Change. Okay? The last way to represent our enthalpy is by, better? Sorry, can you see that better now? Is by an enthalpy diagram, or an energy level diagram. Do you remember these from day 1 of this unit? What is this axis?
That's potential energy.
Potential energy. And time is down here. Okay? So these chemicals here have lost potential energy, become more stable down here as ammonia. See that? And in doing so, the energy they lost to the surroundings was 97.7 kilojoules for the 2 moles that were produced. No, there are 2 moles produced, right? This is not a very lovely diagram. You kind of need those to attach, and those squiggly lines are only to show you that bit there, but we don't actually write it. Okay, so if you had whiteout, get rid of that. So that's per, notice I just have the kilojoules there, not kilojoules per mole, because I'm producing 2 moles. How much is per mole of formation of ammonia? Half of that. So approximately 50, just under 50. Does that make sense? And actually, is this not a formation reaction? And we could look up ammonia in your data booklet, and it should be a little under 50. And it is, because this is per mole of ammonia being formed. This is 2 moles of ammonia being formed. That's why it's twice as much. Everybody see that? This is a good visualization of an exothermic reaction. They're losing energy. By the way, there should be a negative here. Pop a negative in yours. It's losing energy. The chemicals are losing energy. That's why it's negative. So therefore it's exothermic. Chemicals chemicals, loss of energy, whatever. Loss of energy. Okay. Here, same thing, label your diagrams, EP, time. This isn't formation, but now it's decomposition. Again, ignore those squiggly lines. Again, it's 2 moles that are decomposing. And we know that decomposition is the opposite of formation, right? So although this is positive 123.6, in our data booklets, it should be negative because it'd be going the other direction. Negative, and not 2 moles, but per mole. So therefore, approximately 60 kilojoules, not 123. Okay? So, enthalpy is a measurement of energy lost or gained by a chemical reaction. Are you okay with that? Enthalpy is an amount of energy lost or gained by a chemical reaction. We express it in like a whole new language. So this feels awkward. It has positives and negatives depending on whether I mean exo or endo. It has kilojoules per mole or kilojoules, depending if I mean per mole or the whole shebang. Sometimes I mean 2 moles, sometimes I mean half a mole, so I'm going to have to do a little bit of basically ratio conversion to figure that out. And then as if that wasn't enough, they want you to put it inside an equation, sometimes on the left, sometimes on the right, part of a balanced equation. And as if that wasn't enough, they want a picture diagram of it in terms of this graph. But each of them is saying the same thing. Okay, so once you figure out enthalpy, you're good. But it's just asking it in 4 different directions. So to help you out, I've got a little summary sheet here about the different ways of communicating exothermic or endothermic reactions. So what's RXN stand for? Reaction. And so the delta H of a reaction, if it's positive energy, it's endothermic because I'm bringing energy in, I'm adding energy to the chemicals. You can write it like this. You know, blah, 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 space, delta H, positive energy. Okay? Or you can write it like this. A and B take energy in and produce C and D. Or you can draw it like this. A and B put energy in and become C and D, which, by the way, are less stable and have more energy. Everybody okay with that? So that's like a summary of your endothermic. And then below that is a summary of the exothermic. Same thing. Delta H, if standard conditions of your reaction will be negative. I could write it like this. We call this delta H notation quite often. A plus B yields C plus D, space, delta H reaction equals negative number, which is lost. Because energy was lost or produced, we have it as a product within the balanced chemical equation. Or lovely picture diagram where you can see A and B are losing energy and becoming C and D. And again here, I've just shown you it's all about ratios. Right? 2 to 1 to 2 to 1 to 30 is the same thing as 1 to half to 1 to a half to 15. It's just about ratios. That makes sense. If you're burning 1 gram, pardon me, 1 mole, and you're getting 1,000 kilojoules, 2 moles give you 2,000. Okay, so it does take you a while to get your head around the reading comprehension of this. What are they asking for? Okay, you just need to read the question and figure out which method, 1, 2, 3, 4, are they asking, and then do I need to multiply or divide before I go and plug it into my formula or whatever. Okay? So that's what this sheet is going to help you do. It's going to help you undergo your reading comprehension in chemistry and then figure out which way to communicate it. Okay? So we're going to work on this, and we're going to mark this class. And then we'll be done. We might introduce next section because it's always nice to tag it into this, but then we're done. Happy?
Yeah.
Okay, let's go.